Log on, tune in, find out. Another good idea from Cambridge.
Thank you very much. So I know that I introduced lots of notation which you're maybe not used to. So I'm not cheating. I just wrote down notation which we already discussed. So let me just go briefly through it. So Q is a quiver with a set of vertices and arrows. We have a category of representations. We have a numerical approximation to the Grothendieck group given by dimension vector. We make the choice of a functional theta, and that gives us a slope function. With the aid of the slope function, we can define semi-stability and stability, and we have the usual properties. Hardenauer sim infiltration, S equivalence, semi-stables of a fixed slope from a abelian subcategory, and so on. Then we introduced moduli spaces. Our principal example was the moduli space of polystables, which arises as a quotient of this parameter space of all representations, modulo, semi-stable locus, sorry, that I forgot, as the quotient of the semi-stable locus of that parameter space for all representations by the structure group GD acting on it. And it contains as an open part a moduli of stables, which is something smooth. OK, so that was basically the first talk. And yesterday's talk, the Hall algebra. And because we're continuing working with the Hall algebra, I gave the definition again. So we make the choice of K a finite field. So at the moment, we are not doing geometry. We are looking at representations over this finite field. This is a finite set on which a finite group acts. And we are considering arbitrary invariant functions on the set. For these arbitrary functions, G invariant functions, we have a convolution type product f star g of the representation V. Again, V is a representation of the quiver. And the representation of the quiver we can view as a point in this set. Because the representation is nothing else than, well, if we fix the dimension of the vector spaces, then the representation is the same as choosing linear maps for the arrows. And these linear maps for the arrows are encoded in this space or set. Yeah? And evaluating this convolution product on V means summing over all subrepresentation, evaluating F on U and G on the quotient. As a topological vector space, we have a linear basis for the Hall algebra consisting of the characteristic functions of the orbits of this group in here. And the orbits, by definition, were the isomorphism classes. Yeah? So we have a characteristic function for some isomorphism class. And then the product can be expressed explicitly. So we know the structure constants. The structure constants are numbers of subrepresentations of X, which are isomorphic to V with quotient isomorphic to W. So it's something like counting exact sequences with given isomorphism classes. And then we introduce the functions 1 and 1 mu. Function 1 is just constant 1, and the function 1 mu is the characteristic function of all semi-stables of slope mu. OK, and then we produce these identities, like 1 being the product of all 1 mu. So the Hall algebra knows something about the semi-stables. But we have to ask the Hall algebra the right question to get the information out of it. And that's what we'll do now, the integral on the Hall algebra. So definition. Let me define strange ring. This is Q of I. It's something like formal power series indicated by the symbols. So what is this? This is by definition a ring of formal power series in variables Ti, one variable for each vertex in the quiver. That's the formal power series ring. But now we twist the multiplication just a little bit, make it a bit non-commutative. Namely in the following way. Well, if you have variables Ti, then you can form naturally some monomials. So T to the D. T to the D is nothing else than the product over all I, Ti to the Di, the natural notion of a monomial. Yeah? And how do you multiply two monomials in this twisted form a power series ring? Well, the usual definition would be that the product of these two monomials is the monomial to the sum of these two vectors, right? But we twist this a little bit with a factor of q. Namely, this factor of q is coming from the Euler form of the quiver. Yeah? So we form a power series ring and twist the product just a little bit, but making it non-commutative. Because the Euler form, which was Hom minus x, a dimension of Hom minus dimension of x, is non-symmetric in general. Yeah? It's non-symmetric. So this is now a non-commutative algebra, but which still looks like a formal power series ring. And now we will define the following map, integral from the Hall algebra to this slightly twisted formal power series ring. And so this is orbifold integration. A function f is mapped to the following. You sum over all isomorphism classes of representations. Take the value of the function at the representation, divide by the cardinality of the automorphism group of the representation, and multiply by t to the dimension vector.
I'm slightly confused with the fact that you use q there. Is it the same q as the characteristic of the field?
Exactly. Yeah. Okay. So Q, my base field K is FQ. It's a finite field with Q elements, and that's precisely the same.
You make all the terms zero unless the inner product of D and D is zero.
No. I mean Q is something like, well, say 4 for the element for the field with 4 elements. So it's just some power of 4. Well, if Q equals 1, then this would be the usual commutative product, yeah? But, well, in fact, that's actually what's going on in all this, yeah? I mean, there is no field with one element, but you can do lots of mathematics over this non-existent field. And, okay, no, that's a completely different story anyway. Okay, so let me define a map by orbifold, the so-called orbifold integration. And now to get used to this, let's see if we can compute the integral of the function we all like, the function 1. Yeah? And that's in fact a very key example. What is the integral of 1? That is, well, we take the sum of all isomorphism classes of representations, the value of f on this representation, divided by the cardinality of the automorphism group times t to the dimension vector. So that's sum over all isomorphism, so all v up to isomorphism, The value of the function 1 is 1. Divided by the cardinality of the automorphism group times t to the dimension vector. Well, that still, I mean, okay, that's just the definition of this integral. This still looks like something you can never evaluate because we don't know all the representations. But it's precisely this orbifold integration, this denominator cardinality of the automorphism group, which makes this computable. Because now I claim that this is the same as summing over all dimension vectors, taking the cardinality of our finite set, dividing by the cardinality of the group, times t to the d. That's the key thing we have to understand. But I mean, it's really simple. So look at this fraction. Yeah? This means cardinality of the space divided by the cardinality. Oh, okay, I can do it in general. So if G is a finite group acting on a finite set, then what is the cardinality of X divided by the cardinality of G? That's the same as summing over all the orbits of the group in this finite set And it's the sum over the orbits, cardinality of the orbit divided by the cardinality of the group. That's certainly true. Yeah? I mean, X is just the disjoint union of all the orbits. And what is cardinality of an orbit divided by the cardinality of G? That's 1 divided by the cardinality of the stabilizer. So what this is take the sum over representatives of this set theoretic quotient, 1 by cardinality of the stabilizer, Gx. Okay. Well, that's a trivial fact. Let's apply this here. And then you just have to note that the stabilizer in this summation over isomorphism classes, that's precisely the summation over orbits, because we know the orbits are the isomorphism classes. And then you just have to check that the stabilizer is, in fact, this group of automorphisms of the quiver representation. Yeah, that's the explanation for this. Is this little elementary argument. And now this is something, suddenly, this is something completely explicit, which does not involve quiver representations. What is this cardinality? Well, it's a cardinality of a vector space over a finite field. And the cardinality of a vector space over a finite field is Q to the dimension. That group here is a product of GLs, and we know the cardinality of a GL over a finite field. So we can make this explicit. That's the following. Q sum over all D. Q to minus the Euler form of D with D, product over all I and I, product over all K from 0 to Di minus 1 minus Q to the minus K times D. Okay, I mean, just write down what the dimension here, what the cardinality here and here is, and reformulate this a bit, and then you arrive at this. So this is something completely explicit. Yeah? So here you don't have to know anything about quiver representations. The only thing you have to know about the quiver is what are the vertices and what are the arrows, because that's what enters in this Euler form. Yeah? And this looked frightening at the beginning, because it was the sum over all the isomorphism classes, which we don't know. Yeah? But in the end, it turns out to be something explicit. That's something like a Q hypergeometric function, by the way. But okay, I will not discuss this anyway. Okay, so we can make this integral of 1 explicit. Okay, so in a similar way, we could do the integral of 1 mu. So what is the necessary modification? Well, we just have to replace this 1 here in the numerator by 1 if V is semi-stable of slope mu and 0 otherwise. So similarly, you will see that this is the sum over all D, cardinality of the semi-stable locus divided by the, it's 1 plus this. 1 plus sum over all D, which are of slope mu, cardinality of the semi-stable locus divided by cardinality of the group times T to the D. Now, that's something we don't know. We cannot make this explicit easily.
Can you explain what T to the D means?
Yes, T to the D means product of all I, Ti to the Di.
Yeah, did you fix an order of the vertices?
Right. Now, okay, so, yeah. You got me. This is the usual product on this formal power series ring, the commutative one. And now I'm defining a twisted product. You could reformulate this as follows. Take QQi as being topological vector space with the TD as a basis and with this product. That's maybe better than writing it that way, with taking first the usual product and then twisting the product. Yeah? So yeah, that's really better. So we define this as topological vector space with basis certain symbols T to the D, and then I explain how to multiply these symbols. Yeah. Okay, so that's something we don't know. That's something we really want to know. And this 1 is something we know. So now we have our identity. 1 equals the product over all the 1 mu. Wouldn't it be great to be able to integrate this identity? Well, of course we can. Then the left-hand side is something we know. That's this elementary and explicit function. And the integral of 1 mu, that's something we want to know, because we want to know about cardinality of the semi-stable locus. So the only difficulty is that we have to commute integral and product. Yeah? So what we want is to be able to put the integral here. So we have to prove that this integral is an algebra homomorphism. And now that's the very special feature for abelian categories of homological dimension 1. That only works in homological dimension 1 and in the 3 Calabi-Yau case by lots of technical decorations. Or this, yeah. Okay. So let me prove the key fact is that this integral from the Hall algebra to this twisted formal power series ring is an algebra homomorphism. So it commutes with multiplication. And that's one proof I really want to explain in more detail, because you can really clearly see the point where you need that your category has homological dimension 1, at most 1. Yeah? And then, after proving this, I will show you how this identity, which we wrote down yesterday, actually yields an explicit formula for all the Betti numbers of the moduli spaces. Okay, so I will repeat this argument again after the proof of this fact. Okay, so let's prove this. We prove this by integrating these characteristic functions. Yeah? So we have to prove that the integral of 1v star 1w equals integral of 1v star the integral of 1w. And let's see what we have to do for this. Well, okay, so what is the integral of 1v? 1v is the characteristic function just of a single orbit. 1v is characteristic function of a single orbit. So if we integrate it, then we are summing over just one isomorphism class, namely the isomorphism class of v, 1 by automorphism times dimension vector. Yeah? So the right-hand side here becomes 1 over cardinality of the automorphism group times t to the dimension vector of v times 1 over cardinality of the automorphism group of w t to the dimension vector of w. That's the right-hand side. But now note that this product here, that's the little twisted product in this twisted formal power series ring. Yeah? So, and this in turn then equals q to the minus Euler form dim w dim v divided by the product of the cardinalities of automorphism groups dim v plus dim w. Okay, so the only thing happening here is that from this product of t to the dim v and t to the dim w, we get this extra factor q2 minus the Euler form. Yeah? Because that's our little twisted multiplication here. So that's the right-hand side of this equation. What about the left-hand side of this equation? The left-hand side, well, we can first evaluate 1v star 1w, this product, explicitly. That's still written here. That's involving the structure constants of the Hall algebra, and then we can integrate. Yeah? So this is nothing else than take the sum over all x, cardinality of the set of subrepresentations of x, such that the subrepresentation itself is isomorphic to V, with quotient isomorphic to W, times the integral of 1x. Well, we make this integral linear, of course. Yeah? So we can apply the integral to this identity, and then we have integral of 1x. And this here is then sum over all x, cardinality of the set, times the integral of 1x, which is again of this form. 1 divided by odd x times t to the dim x. Now that's the two things we have to compare. So I promise this will be the last difficult calculation for today. After that, we'll be more structural again. But we have to see this. OK, so this is the identity we have to prove. And now this works as follows. We already saw that this crucial cardinality, the structure constant of the Hall algebra, this has something to do with counting exact sequences. Now we have to make this precise. We have the following diagram. So here, I really literally take the set of exact sequences. So I take the set of maps. So these are maps of quiver representations again. Yeah? We take the set of pairs of maps alpha from V to X, beta from X to W, such that this gives an exact sequence. So alpha is injective, beta is surjective, and kernel of beta equals the image of alpha. That's taken literally the set of exact sequences. Now here we put the set which is the structure constant in the Hall algebra. The set of all subrepresentations which are isomorphic to V with quotient isomorphic to W. That's something we want to know about. And on here, I put another set. X1 WV index X. Now I have to explain what this is. Well, X1 you can usually calculate by some projective resolution, but there's also an explicit definition for X1, namely take the set of exact sequences with respect to a certain equivalence relation. Yeah? And you know this equivalence relation. So if this is an exact sequence, short exact sequence, and this another one, they're called equivalent if you have a commutative diagram with an isomorphism here and identity maps here. That's the notion of equivalence for short exact sequences. That computes X1 for us. And now X1 index X means taking all the exact sequences whose middle term is isomorphic to X. Because in this whole set of X1, a priori don't specify the isomorphism class of the middle term. It might be a split exact sequence, and the middle term is just the direct sum. Yeah? So exact sequences with middle term isomorphic to X. So these are three finite sets, because we're still working over a finite field. Now, what is the connection between these sets? Well, we have lots of groups acting on here. On this, you have actions of the automorphism group of V, the automorphism group of X, and the automorphism group of W, multiplying alpha and beta from the right or from the left. Yeah? So here you have an action of odd V cross automorphisms of W, And on the other hand, you have an action of the automorphism group of X. And can directly work out how these actions work. Now, the action of odd V and odd W, this action is free. Because this is an injective map. And if you multiply this injective map by an automorphism here, then you get the injective map again, if and only if you multiply by the identity, because it's injective. Yeah? So this is a free action. Free. This action by odd X, that one is not free. It has a stabilizer. And the stabilizer of this action is the following subgroup of the automorphisms. 1 plus alpha homomorphisms from W to V beta. This requires a little bit of very simple diagram chasing. Yeah? But, I mean, corresponds to the realization of X1 as 1 co-cycles modulo 1 co-boundaries. And these correspond to the 1 co-boundaries. Yeah, so that's actually, it's not difficult. So now what happens if you factor this set of exact sequences by the odd V times odd W action? What does the exact sequence remember if you allow action here and here? It doesn't remember the actual map alpha, because you're multiplying this map alpha by some automorphism of V. The only thing it remembers from alpha is the image of alpha. Yeah? The only thing an injective map remembers if you apply automorphisms is the image. And also here, the only thing that is remembered from beta is the quotient. So if you take the quotient by this free action, you arrive precisely at this set. So this is a quotient by odd V cross odd W. On the other hand, what happens if you mod out by the action of odd X? Well, that's precisely the definition of X1 as equivalence classes of short exact sequences. Yeah? You mod out, you allow isomorphisms of the middle term, but you do not allow isomorphisms of the outer terms of the sequence. So taking the odd X quotient of the set gives you the set of the subset of X1. So this is a quotient by odd X. Okay, and now again we can count. So what we want to know is that the left-hand side equals the right-hand side. Yeah? Okay, so let's take our left-hand side and replace the cardinality of this strange set by something else. So left-hand side of our desired equation is sum over all x, cardinality of this set of u in x, u isomorphic to v, x mod u isomorphic to w, times 1 by automorphism group of x, times the dimension vector of x. Now how to rewrite this cardinality? Look at this diagram. The cardinality of the left-hand side is the cardinality of the top thing divided by the cardinality of the group we are factoring. On the other hand, the cardinality of this top thing is the cardinality of this X1 space times, not times the cardinality of odd x, but odd x divided by the cardinality of the stabilizer. So anyway, what counting in this diagram gives you is that this is the same as take the cardinality of the set of extension classes with middle term isomorphic to x, multiply by cardinality of the fiber of this map to the right, which is cardinality of odd x, divided by the cardinality of hom, and then divide by the cardinality of the fiber of the left-hand side, which is odd v times odd W. Now we are almost there. So this looks complicated, but now it drastically simplifies. And so lots of things cancel. And we have to see how everything cancels. OK, so first of all, we have all x appearing here and here. So they cancel. Look at all the terms which are remaining. All these terms here in the denominator do not depend on x. Yeah? And also the dimension vector of x is independent of x. Because if you have a short exact sequence, then the dimension vector of x is the sum of the dimension vectors. So I can replace this by dim v plus dim w. So if we pull out everything which is not dependent on x, then what's remaining is t to the dim v plus t to the dim w divided by automorphisms of v times automorphisms of x times homomorphisms w to v, sum over all x, cardinality of the set of extension classes with middle term isomorphic to x. So, and again, this simplifies. So what's this? We're taking the set of all extension classes with middle term isomorphic to x. But then we are running over all x. Yeah? So that's nothing else than all extension classes. I used two different symbols for indicating cardinality. That's somehow bad. So, OK, so by definition, x means x. Sorry for that. OK. So now what is this cardinality of x1 and what is this cardinality of Hom? Well, Hom and x1 are again vector spaces. Yeah, so their cardinality is q to their dimension. So I can erase these two terms. And replace it by q to dimension of x1 minus dimension of Hom. Yeah? It's the quotient of the cardinality of two vector spaces, which is q to one dimension divided by q to the other dimension. OK, now that one we know. That's the Euler form. Yeah? That's precisely the Euler form of minus the Euler form of dimension vector of w, dimension vector of v. So at the end, after all these cancellations, what remains is t to the sum of the dimension vectors divided by product of the cardinalities of the automorphism groups times q to the minus Euler form. And that's precisely the right-hand side of this equation. Yeah? So we proved that the integral is an algebra homomorphism. But now you see the absolutely crucial point why we need an abelian category of homological dimension 1. I mean, this calculation here, that works in every abelian category. That's completely general. Yeah? Has nothing to do with homological dimension 1. The only problem is, in general, this difference here, dimension of Hom minus dimension of x1, or the other way around, that depends not only on the classes of v and w in the Grothendieck group. Yeah? So for example, if you have a category of homological dimension 2, then it's dimension Hom minus dimension x1 plus dimension x2, which factors through the Grothendieck group, but nothing else. Yeah? So if this depends on more than just the classes in the Grothendieck groups, then we cannot have it as a factor in here. We cannot make this into some nice twisted ring, because that wouldn't be well defined. It really depends not only on the dimension vectors. Yeah? So that's the reason why everything here only works for abelian categories of homological dimension 1. And, well, something is possible in the 3-Calabi-Yau case, because the 3-Calabi-Yau case somehow pretends to be of homological dimension 1. No, that's nonsense, but anyway. So in the 3-Calabi-Yau case, you have a duality between 0 and 3, and a duality between 1 and 2. So again, if you know x0 and x1, well, then you already know x2 and x3. Yeah? So that's special for the 3-Calabi-Yau case. So for that reason, you can expect that something similar might work in the 3-Calabi-Yau setting. But this method itself directly only works in the homological dimension 1 setting. OK, so now let's stop to do all these calculations and come to some results. Yes, I can erase this. If you don't like this proof, then just believe that this is an algebra homomorphism, and then we can continue. So now to Betti numbers and numbers of rational points of these moduli spaces of theta, stables or polystables. Okay, so we start with the identity. 1 equals descending product over the rationals of 1 mu. Identity in the Hall algebra of the quiver. And that was the essence of, well, essentially this was just the existence and uniqueness of the Harder-Narrow sim infiltration. Now we integrate this identity. Then we get integral 1 equals product, descending product over the rationals, integral of 1 mu. And that's the crucial step, that we are allowed to exchange integral and product. That's why we need that this is an algebra homomorphism, and that only works for homological dimension 1. Now that's an identity in our skew formal power series ring. Okay, so let's make this identity explicit, because these two integrals we have already computed. It's on top here. The integral of 1 is this Q hypergeometric function, and the integral of 1 mu involves cardinality of these semi-stable loci. So we get that this sum over all d, q to the minus dd, divided by product over all I, product over all k, 1 minus q to the minus k, t to the d, equals descending product over the rationals of the power series 1 plus sum over all dimension vectors which have slope mu, cardinality of the semi-stable locus over our finite field K, cardinality of the group, G to the D. So that's just plugging in the two explicit formulas in this identity. This I, this is what's written there. It's the product over all vertices. Okay. So first take the product over all vertices of the quiver, then take the product over k running from 0 to di minus 1, 1 minus q to the minus k. So that should be precisely what I've written here. Yes. Okay. So this we don't need anymore. So what does this identity tell us? Yeah? So you have one formal power series expressed as the product of infinitely many power series. Now compare coefficients. Yeah? And comparing coefficients, you get a recursion expressing this coefficient in terms of these explicit coefficient. So that gives the recursion, which I will show you later in a resolved form, a recursion expressing the cardinalities of the semi-stable loci over finite fields in terms of the coefficients on the left-hand side. Yeah? In terms of coefficients on the left-hand side of this identity. So it's a huge recursion, okay? But anyway, this is something we do not know explicitly, and we have a recursion expressing it in the coefficients of the left-hand side, which are something explicit. It's just q to some power divided by 1 minus q to something, product of 1 minus q to something. That's simple. Okay, so why is this interesting? Okay, and now we come back to geometry of the moduli spaces. Yeah? So far, this was abstract Hall algebra things. What we just need is an abelian category of homological dimension 1 over a finite field with a slope function giving us semi-stability. Yeah? So up to now, everything is possible for A homological dimension 1, A over a finite field FQ, and with a chosen functional theta. But what does this have to do with geometry? Okay, now we come back to our moduli spaces. We want to know Betti numbers of moduli spaces. What we know is something about points over rational points over finite fields. What is the connection between these? Well, that's Delign's theorem, the Weil conjectures. If we have a smooth projective variety, then we have a relation between the Betti numbers in singular cohomology and number of rational points over finite fields. Yeah? And that's what we use now. So with this arithmetic trick, we can compute the Betti numbers using points over finite fields, and these we get with an explicit recursion. Now we make one assumption. So assume that, so the following only works in the coprime case. That D is coprime, so D is not a proper multiple of another dimension vector, and theta has to be somehow generic, so avoiding finitely many hyperplanes in stability space. No, not stability space. Theta is just a functional on the numerical Grothendieck group, avoiding finitely many hyperplanes in this space of functionals. I don't claim this to be related to Bridgeland space. Okay. Then we know that the moduli of polystables is the same as the moduli of stables because there are no properly semi-stables. As in the vector bundle case, if rank and degree are coprime, then every semi-stable is already stable. Yeah? So then we have this identity, and this is in fact okay, so polystable is the same as stable, and we also know that the semi-stable locus equals the stable locus. And this here is a PGD principal bundle. This quotient map. That was the quotient map. And so in this situation, what you can get is, well, okay, so that's one ingredient. The other ingredient we need is that, well, we defined these moduli spaces over the complex numbers. We somehow want to have a passage from moduli spaces of the complex numbers to something over finite fields. So we need something like an integral model for the moduli spaces. So fact, there exists a scheme curly x over the integers such that the base extension to the complex numbers of this x is nothing else than our moduli space of stables. Yeah? So the moduli space descends to the integers. How do you do this? Well, this moduli space is nothing else than the quotient of this vector space of all representations by this group. And all this can be formulated over the integers. And then you apply Seshadri's integral variant of GIT to get this approach of a semi-invariant ring over the integers. Yeah? So everything can be done over the integers because there are no non-trivial coefficients involved. Yeah? So this actually means everything can be done over the integers. And then we can reduce to finite fields. Yeah? Then we can reduce to finite fields k. So we can take this x and look at k rational points. And that's the numbers we're interested in. OK? So that's the two geometric ingredients we need. First of all, if we are in this coprime case, then we have this principal bundle. So then the moduli space arises as the geometric quotient of the stable locus by the group PGD. And other fact, everything can be modeled over the integers. Now let's combine this. And then we get the following, that the cardinality of this xk, so that's our reduction of the moduli space to a finite field. That cardinality is the cardinality of the stable locus over the finite field divided by the cardinality of the group PGD over the finite field. Yeah? So this is our moduli space, now defined over finite field. And it arises as a geometric quotient. And in this special case, in fact, we have this identity. Now, what is the cardinality of PGD? Well, PGD was the group GD modulo scalars. Yeah? So this is nothing else than Q minus 1, cardinality of the scalars, times cardinality of the stable locus divided by cardinality of the group. Again, since we are in the coprime case, it doesn't make a difference if we write semi-stable locus here. So, but this is something we know by some explicit recursion, which we get from this identity. Yeah? So, and now from this recursion, you can actually see that the cardinality of rational points over finite fields of this moduli spaces behaves like a polynomial in the size of the field. Well, actually, first of all, it's a rational function in the size of the field. Yeah? So x of k is given by this. This is given in terms of a certain recursion. And this incursion involves these coefficients here. And these coefficients are clearly rational functions in k. Yeah? So everything is a rational function in cardinality of k. Is a rational function in the cardinality of k. And now there are some general facts. If you have a variety or a scheme such that the number of rational points over finite fields is counted by a rational function, then it's in fact counted by a polynomial with integer coefficients. Actually a polynomial with integer coefficients. And if this variety is smooth projective, or more generally cohomologically pure, then this polynomial is the Poincare polynomial in singular cohomology. So here we need that the moduli space is smooth projective, which is, yeah, okay, let me first write this down. So this is then sum over all I, dimension of the ith singular cohomology with rational coefficients times, that's a funny thing, q to the 1/2. So that's a consequence of the Weyl conjectures. Yeah, so this is easy, and this requires Weyl conjectures. Now, this q to the I/2 looks strange, right? Well, this automatically tells us that all odd cohomology vanishes. Yeah? There is no odd cohomology, only even cohomology appearing, so I can use the power q to the I/2, and this polynomial, this Poincare polynomial, is the polynomial counting rational points. And then we see, after that, well, this is a polynomial with non-negative coefficients. So actually, everything is counted by a polynomial with non-negative coefficients. OK. So now I should formulate the final formula. But before I do this, let's again somehow follow the logic of that argument. I mean, all this is, well, somehow it's nothing new. I mean, it's precisely Harder-Narasimhan for the vector bundles on curved case. So this is precisely Harder-Narasimhan, just decorated with this Hall algebra, which makes things look nicer somehow. Yeah? So we produce a nice identity in the Hall algebra. And this identity in the Hall algebra is equivalent to Harder-Narasimhan recursion. Then we need to find a way to get useful information out of the Hall algebra. That was our integral. Applying the integral gives us a recursion expressing this stacky count of semi-stable points in terms of something explicit. Now, in this favorable case of a coprime dimension vector, stable equals semi-stable, moduli is smooth projective, so there's a chance to apply Weyl conjectures. To get the Weyl conjectures, we first take our complex moduli space, realize it over the integers, so that we can specialize to finite fields. Over finite fields, it follows from our recursion that everything is counted by a rational function and then automatically by a polynomial. Then the Weyl conjectures tell us that this polynomial is the Poincare polynomial at the end. So here's the final formula after all this. So when do I tell you about the 3 more chapters I prepared? Oh my God. OK, so here's the final result. So there's one more thing one can do. Well, that gives a recursive formula. One can resolve this recursion. In the case of vector bundles on curves, there is the resolution of the Harder-Narasimhan recursion by Zagier, which is really ingenious because it involves induction over the reals. So that's really crazy. In the quiver case, it's much, much simpler. One can resolve this recursion, and the final formula we get is that the Poincare polynomial, so D coprime, like before, yeah? So this is the coprime case, that the Poincare polynomial in singular cohomology with rational coefficients is q minus 1 times the sum of all decompositions of the dimension vector with certain properties, minus 1 to s length of the decomposition minus 1, q2 minus sum over all k less than or equal L, Euler form of dl dk, product over all k from 1 to s, product over all vertices, product over all whatever, j from 0, it doesn't fit on the blackboard, what a pity, times product over all k from 1 to s, product over all vertices, product over all j from 0 to dki minus 1, 1 minus q to the minus j, where, and now I only have to specify the sum over all ordered decompositions of our dimension vector into a sum of non-zero dimension vectors, and where the slope actually fulfill the following condition, that the slopes of all partial sum should be strictly greater than the total slope. Okay, so the details of this formula are maybe not so important. Let's just look at it without all these indices. So what's this? So on the left-hand side, we want to get the Poincare polynomial. It's a polynomial with non-negative coefficients, because coefficients are dimensions of vector spaces. What do we have on the right-hand side? We have a huge sum. Sum over what? Well, first of all, this sum involves a sign. Then it involves a power of q. And then it involves a huge denominator. Sorry. A huge denominator with terms 1 minus q to something. Yeah? So this is an alternating sum. So it's a sine sum of q to something divided by some denominator involving 1 minus q to minus j. Yeah? And so the right-hand side is only a rational function. And there's no way to see on this right-hand side that this is a polynomial with non-negative coefficients. But we know that after performing this summation, somehow by pure magic, all the denominators cancel away. And what we get is a polynomial with non-negative coefficients. That's really pure magic. Yeah? In particular, what you can get from this formula is all the individual Betti numbers, but you cannot get the Euler characteristic. What is the Euler characteristic? The Euler characteristic is the value of this polynomial at q equals 1, because there's no odd cohomology. But on the right-hand side, you should never plug in q equals 1, because you have all these denominators here. Yeah? So every summand has lots and lots of poles at q equals 1, but they somehow magically cancel away in the summation. Yeah? So that's the final outcome of this procedure. And there are some more formulas, but there's no more time. So I think I should stop here. Thank you.